the largest methane gas leak in U.S. history.
The 2015 Aliso Canyon leak forced thousands of people from their homes.
Imagine sitting in your home when a foul odor suddenly fills the air. Soon, you start experiencing unusual nosebleeds, headaches, nausea, and other troubling symptoms. This was the reality for communities near the Aliso Canyon natural gas storage facility when a blowout released over 100,000 metric tons of methane into the atmosphere. Though this event was labeled the largest natural gas leak in U.S. history, a more concerning silent threat still lingers in oil wells across the country. The United States has a documented history of over 4 million oil wells drilled since 1859. However, the Interstate Oil and Gas Compact Commission suggests there are an additional 300,000 to 800,000 undocumented wells. Of these, just over 900,000 remain productive, leaving an estimated 3 to 4 million idle or abandoned, often leaking potent greenhouse gases and harmful toxins with little to no monitoring. The Environmental Protection Agency reports that abandoned wells contribute around 280,000 metric tons of methane emissions annually. Research from USC shows that leaks from urban oil fields near their campus pose health risks comparable to passive smoking or residing near heavy traffic. The Inglewood oil field, one of the nation's largest urban fields, covers 1,000 acres with over 1,600 wells. Over 1 million residents live within a 5-mile radius of this field, with some community advocates arguing that noxious emissions from the field are causally linked to cardiovascular and pulmonary diseases, cancer, congenital disabilities, and increased mortality rates. Despite serious health and environmental risks, there is no ongoing initiative to systematically measure emissions from the Inglewood field or nearby communities. To tackle this problem, we set out to develop an affordable yet effective solution. Our answer is a mobile Internet of Things, or IoT, device that can be mounted on road vehicles to measure methane concentrations in that specific area. To detect methane, we use the MPS Extended Range Methane Gas Sensor. This sensor can not only detect methane in ppm, but also measure ambient temperature and pressure. These two parameters are considered crucial for future methane research as well. To interact with this sensor, a microcontroller is necessary. This is the Odroid M1S microcontroller, a powerful device with 4 GB of memory and 64 GB of storage, ample for transmitting data from IoT sensors. Despite its embedded functionalities, the peak power consumption is only 3.5 watts, making it very energy efficient for long-term use. Most importantly, there are numerous open-source resources available in the community, making it easy to develop with. This is the pin allocation showing how the sensor is connected to the Odroid board. Communication between the sensor and the board uses UART. Through UART communication, the sensor sends raw hex data to the board, which then converts it into decimal values by the microcontroller. After processing the data, the Odroid board needs to send it to the cloud. We used a well-known IoT cloud hub called ThingsBoard. Transmitting data to it is straightforward. You can even use HTTP post to upload the data. As shown in the image, the data is stored with a key name and corresponding timestamp. Each device has its own token, ensuring that all data is sent to the correct target. It is easy and secure to use.
For the physical design of the sensor cover, we used a PVC pipe, poly-distribution tubing, a solar battery pack, metal cup, methane sensor, sensor board, and a micro-diaphragm pump. Inside the PVC pipe cover, we installed the pump, sensor board, and tubing. The tubing connects to the pump with one tube extending outside the cover to intake air, and the other tube passing through a hole at the top of the cover. This tube leads to a cup containing the sensor, which is mounted on the exterior of the cover to direct air towards the sensor while shielding it from the wind. The outer cup features a top hole to ventilate methane after it has been detected by the sensor. Additionally, the cover houses the processor and pump to protect them from the wind generated by the moving car. A solar-powered battery pack is mounted on top of the cover to supply power to the processor and pump, utilizing solar energy captured from the car's roof. Also, in this design we have used red duct tape to hold some of the materials in place, however, in a final product they would be glued down. Finally, to mount the sensor on top of the car, we used a strong rope, a foam pad, and a crank system. We threaded the rope through the center of the PVC cover, where we had made 2 holes on opposite ends. This rope was then placed in the crank system and tied inside the car. The cover was also placed on a foam pad to protect the car's roof. When cranked and secured inside the car, The cover compresses into the foam pad, minimizing the impact of wind or excess air that could interfere with the results. Once mounted, we were able to drive with the sensor to collect data on temperature, pressure, and methane.
After collecting the data outside, we now need to download and analyze it. As mentioned in the previous section, each device has its own data with timestamps. These two images show the raw data from two different devices recorded during different time periods on the same path. Here is how we process this raw data. The first step is downsampling the GPS data. Since the driving speed is not constant, some areas may have more signals, while others may have fewer. Downsampling ensures that the GPS signals are evenly distributed on the map. This image shows the raw data we collected. And these are the points after downsampling. Once we have the downsampled GPS signals, we can record the average sensor data from the square region around each signal onto that signal. Since we have multiple samples taken at different times, the average sensor data from each sampling time within this square region is recorded onto the downsampled GPS signal. This way, we obtain a set of average sensor data at different times for each GPS point, representing the data levels within that square region. The final processing step is to use a heat map to represent the sensor value levels after processing the previous steps. Here are two images showing the same measurement path at two different times. We can see there are significant differences. Since we cannot measure the entire region whenever we want, we use the collected sensor values to interpolate the sensor values at the same location but at different times. This allows us to create a timeline for a specific region, showing how the sensor values change over time. This is the result after all the data processing. The heat map timeline shows the temperature changes between the start and end of the measurement period.
When comparing mobile and stationary sensors, mobile sensors present several notable advantages. Stationary sensors require state and city permits for installation on homes, which can introduce various complications. Additionally, cost considerations play a crucial role in selecting the most effective data collection method. Each stationary sensor, priced at $250, covers up to 100 square meters. To adequately cover the entire city of Inglewood with sensors installed on homes, about 235,868 sensors would be required, resulting in an estimated cost of $59 million. This estimate also does not account for additional expenses related to sensor functionality such as covers and pumps. In contrast, our mobile sensor system, which includes a functional cover and pump, costs around $300. This system requires only a few vehicles and the algorithm we developed to achieve the same data collection. Mobile sensors are easily installed on vehicles and can efficiently cover larger areas, enabling data collection across various locations and times. Overall, mobile sensors are the better choice, as they are not only cost-effective, but they offer accuracy and flexibility in data collection.